on parallel operation of synchronous generator, and we will understand today how to use a 3-lamp method to synchronize a synchronous machine to a infinite bus bar. Now let's look at this diagram first. Here we have a 3-phase synchronous generator. This is my generator. I have represented the 3-phase voltages of the generator as EA, EB, EC, and the grid voltages as VA, VB, VC. We have measured the terminal voltage of the generator and the grid, and by controlling the field current we have adjusted these two voltages to be same in magnitude. Now the next question is that we have to ensure that they are in same phase and their frequency is also same. So to do this we will use a 3-lamp method. Here you can see that one lamp is connected across A phase of the machine and A phase of the grid. The second lamp is connected between B phase of the machine and C phase of the grid. Please note that it is connected between B phase of the machine and C phase of the grid. And the third lamp is connected between C phase of the machine and B phase of the grid. Now this connection is referred as the 3-lamp connection. Now before we go into this, how this connection of lamp helps us, let's understand little bit about what happens when these two are at different frequency. Let's say that at some instant of time my generator voltage is, I am showing one of the phase of the generator voltage. The other phase we will understand that B phase will lag A phase by 120 degree and C phase will lag B phase by 120 degree. So we have drawn only for A phase. The B and C phase are well understood that they are 120 degree lagging. Now at some instant of time, let's say that this is my generator voltage by blue line and the red line is showing me the grid voltage VA. Here the grid voltage is lagging the generator voltage by some angle. How to represent it in a phasor diagram? If this is my voltage of the machine, then the voltage of the grid will lag this one by some angle, that is this is VA. So if this is EA, EB will be somewhere here. This is my B phase voltage which I have not drawn here but it is there, and this is the C phase voltage, this is EC. Similarly, if this is VA, this will be my VB and this will be my VC. Now can we combine these two diagrams together? If I combine these two diagrams together, it will look something like this. If I combine these two, then this will remain as EA, that is my generator voltage EA. This will be EB. This will be EC. Now my grid voltage will lag this one by some angle. So this will be my VA, this will be my VB, and this will be my VC. Now let's look at another condition. Here both VA and VB are in same phase. How this has happened? Let's say that my incoming generator is slower than the grid, okay, or the grid is faster than the incoming generator. Both the statements are same. Let's say that my incoming generator is slower than the grid. Then what will happen? The incoming generator is slower than the grid. That's why the voltage will slowly lag behind, and after some time it will come in phase with the grid voltage. So initially it was here. After some time, since it is slower than this, these two phase will come in phase with each other and they will be in the same phase. This is shown here. So here the incoming generator is leading the grid voltage, and from here if after some time it comes to this position, it means that my incoming generator is slower. That's why this has lagged to this. That is, previously this was lagging, after some time it has come in phase, so this is slower. What will be the phasor diagram in this condition? In this condition the phasor diagram will be, this will be my EA, this will be my EB, this will be my EC. This is for the incoming generator, and the grid voltage will again be in the same phase. So this is VA, this will be VB, this will be VC. So you can see that at this instant of time the phasor diagram is like this, at this instant the phasor diagram is like this. Now look at another condition. If the incoming generator is faster than this, then what will happen? If the incoming generator is faster, then the phase difference between these two will further increase. In that case, the phasor diagram will now look like this. This is my incoming generator EA, EB, EC. If it is faster, if this is the initial condition, if the incoming generator is slower, it will be like this. If the incoming generator is faster, then this phase difference will increase further. What I want to conclude from these diagrams is that since the frequency are not constant, the phasor diagram will not remain constant throughout the operation. The phasor diagram will change with respect to time. As the time changes, the phasor diagram also changes. That's why in our last class we say that we can only draw a phasor diagram if the two frequencies are constant. If the two frequencies are not constant, then the phasor relation or the phase shift will change. As a result, the phasor diagram will also change. Now let's look at how this information about these things helps us in finding what is the frequency and what is the phase of this generator. Now let's look at a condition. Now let's assume that at any instant of time the the phasor of the grid voltage and the generator voltage are in same phase. That is EA, this is EA, EB, and this is EC, and VA, VB, and VC, they are in same phase. Their magnitude is already constant. How we have made the two magnitude constant? By adjusting the field current. We have measured the magnitude by a voltmeter and we have used the field current to make sure that these two magnitude are constant. So magnitude of this and this is constant. At some instant, say that this frequency is not equal to this frequency, then the two phasors are continuously changing. At some instant it is like this, at some instant it is like this, at some instant it is like this. So the phasor relation between EA and VA is continuously changing. We are taking a particular instant of time when the situation is like this, that is EA and VA is in phase. So I have drawn the phasor diagram once again when EA and VA are in phase. Let's look at what happens to these bulbs. When EA and VA is in phase, then this lamp L1 will glow, will be dark. Lamp L1 will be dark. What do you mean by dark? It means that it will not glow. Why it will not glow? Because the voltage here and the voltage here is same in magnitude and in phase. You can see there E and V are same in magnitude and phase. That's why the voltage here and the voltage here will be same, and as a result this bulb will not glow. What about lamp L2? Lamp L2 is connected between EB and VC. You can see this is VC and this is EB. So this lamp is connected between EB and VC. You see here EB is along this line, VC is along this line. So there exists a voltage difference between this. What is the voltage? It is nothing but the difference of these two, which is like this. So though the voltages are same in magnitude, but they have a phase difference for which this lamp L2 will glow. We will write it as L2 is bright. What about L3? L3 is connected between E3 and this is VB. So VB and EC, that is between this voltage and this voltage. Again they are at a different phase, so there will exist a voltage. That's why L3 will also be bright. So under this condition this lamp will be dark, it will not glow. This lamp will be bright, it means it will glow, and this one will also glow. Now let's take a condition when the incoming generator is faster than the grid. So what will happen? The grid voltage will remain like this. I take grid as reference, that's why I keep this along this line. So this is VA, this is VB, this is VK. So incoming generator is faster. What does it mean? It means that after some time EA will lead VA, this will be EA, this will be EB, and this will be EC. So what will happen now? Now all the bulb will glow, because between this and this there is a voltage difference. Between EB and VC, EB and VC there is a voltage difference. Between, sorry, this is EC. Between EB and VC there is voltage difference. Between VB and EC there is voltage difference. So all this will glow. Now if this continues to rotate, that is if this difference in frequency exists for a finite amount